So this is a flavour of some of the work that we've done in ARUP in London, just to give you a feel for what we are using it for as a designer. So these are a range of project types that we have, all of them being steel apart from the Sydney Opera House, but I had to get that one in. So all these are steel structures that have exposed visible connections predominantly, and so we have to have a way of being able to design these in as quick and as simple a way possible. So what we were after was a tool that was allowing an efficient workflow, so that involves interoperability with all the other tools that we use, be it advanced steel or Tekla structures. I have to say that once. Be simple and easy to learn, and fully supported by codes and validated. And you've heard already some of that validation that's gone into this tool. There's a tremendous amount of effort that's gone on by the guys that have got this tool together. And also, we want a tool that's used from the early stages of projects to help with feasibility and buildability studies, all the way through to detailed design studies. So I'm going to show you a few more examples in a second. To us, from the UK, it's a tool that's uses Eurocode, but it also uses the American AISC, so that you've got the ability to use it to either code. But in particular, in the Eurocodes, there's the parts 5 and 6 of Eurocode 1993. So that's Appendix C in that, or more correctly, Annex C, deals with plated elements. And there's also part 6 to the Eurocode 3, which is about shell structures. And so the tool uses both of those. And I would suggest it's well worth the read, particularly the bit in the part 5 here, which is about needing to understand how finite elements work in your design tools. So it's a good read. It's not a particularly long read, but it helps understand what the tool is trying to do. So that's one thing I'd recommend. So some examples of its use. Now, 10 years ago, this is the Leadenhall Tower in the City of London. And the nodes that we were analysing and creating there, that's one particular node that's about 3 meters from top to bottom, channeling huge amount of force through the plated elements. So we had to go through that in quite a complex way 10 years ago, which involved Nastran analysis and LS-Dyna stress plots to work out welds. So we still use a lot of this methodology, but what we've got out of this tool is a much quicker, simpler way to analyze the likes of a node like that. We were also being able to create weld plots, looking at different load cases. But this tool, the StatiCa connection tool, is able to produce all of this in one output and very quickly as well. So now, this is an example where on the bottom left is the stress plots from the tools that we would normally have used, which is LS-Dyna. And that's looking at a particular tubular structure with a strut. So you can see that in the top of the image. There's a strut coming down there, fixing up to a tube. And so the reason this came to us was because the connection was unstiffened, and we had to look at how this connection, taking all the loads into an unstiffened box, was going to behave. And we found quite good correlation in how we were doing it before to the tool that we used in this. And in fact, the inputs are slightly different in the two analyses, so it's not a direct comparison, unfortunately, but nevertheless, we were pleased to use this. And we were also looking at 270 load combinations in one go. Part of the problem of enveloping results, as engineers, you probably grapple with this all the time. You have to either envelope all the results and provide one set of forces, or you look at all the possible load combinations, including pattern loading. So here, the tool is able to go through each and every one of those load cases very quickly, and so we use that to help home in on which were the most appropriate load cases to consider in more detail. And here's another example. This was a bit more forensic analysis. We were called to a contractor's site where they were seeing the ends of a truss cord, which is to the right of this image, which was a cantilever. They were seeing that cantilever deflect quite a lot. And all the force in the tension in the top cord, which is shown up on the right here, was being channeled down the brace behind it. And we, from the visual site inspection, were able to see that this connection was probably one of the reasons the contractor was observing quite large deflections in the cantilever. So we looked at this in the tool, and from the geometry that we knew, we were able to apply the various manufacturing operations as described already, and develop a very simple connection. And this is, when you're familiar with the tool, it takes about 20 minutes to do this, or maybe even less, in fact. but then you can analyze it and interrogate the results, which is the important bit. And so this was the stress results, and as you can see on the left, all the plates have a tick here, so that statically this connection was doing all it was being asked to do, to channel the forces. The problem came when you look at the deflected output from this connection. So if you remember, there was a tension force in this top chord, which was having to be resisted by the brace. So all the plates were being pulled apart, and it wasn't a very stiff connection. And you can see that by the way that the connection was opening up. And you can see particularly top right, there is an end plate on this connection here, which is a tube, and that end plate was bolted below. Also, this was a PFC, a channel section, with the bottom web part being pulled down by the gusset attached to the brace. More obvious as you toggle through it. So the StatiCa also has the ability to look at the stiffness of a connection. So that is the stiffness plot, clearly showing the weak links. So there's the end plate on the right and then a part of the end plate on the top. This was not a very stiff connection, which was it was very obvious to us on site because it was what we went to have a look at, or my colleague. But the tool could have been used or should have been used much earlier in the project by the person that did that connection, and that would have immediately shown the logic of what was wrong with that particular connection. So another couple of examples. This was a plate where hidden inside of it were lots of stiffeners, and we were looking to see whether the stiffeners could have been removed or reduced in size, and we were able to conclude that the stiffeners were about double the thickness that was needed, so we halved those, which worked well. So a few more examples just to wrap up. Tubular structures with bolts, so we've been using it to look at those for welded connections as well as bolted connections. We're using it with advanced steel to link to a roof cord, as you can see here. So on the left is advanced steel, and on the right is the output into StatiCa, which this is hot off the press, so this is being analysed at the moment. And then a couple of other examples of the sorts of things we produce, where these connections, this one and this one as well, we as engineers have to know that what we're providing is fully buildable and designable. There's no point in offering up a connection to a contractor to design if that isn't the case. In many of the examples I've shown, we are, as an engineer, responsible for those connections as well. So the workload spreads the whole gamut of us being, as engineers, responsible or the contractor being responsible. But ultimately, we have to know that it's buildable. So the tool allows us to take the output from, say, an advanced steel model and very quickly run through those options.